Welcome to part 2 of our series Area from a Calculus Perspective, where we will be finding the area under a curve using the limit definition. Now, before we get to that definition, we are going to be finding the solution to this task. The task is to find the area of the shaded region. Now, what I recommend in this video is that you put down your pencil, just watch and pay attention. I will let you know when you truly need to write something down. We are going to be figuring out the area under a curve and the limit definition to find it through this first simple task. Now, we do not really know how to do this yet. This is literally a curve. It is not a straight line where we could just use geometry to find the area of a triangle or a rectangle. Let's see if we can figure out what this function is here in black. Well, it looks like it has the points 0, 0, 1, 1, and 2, 4. It looks like this is the curve f of x equals x squared. And we only want to find the area under that curve down to the x-axis between the x values of 0 and 2. So here's our task written out in a more specific way. This shaded region in blue is really the area under the curve f of x equals x squared down to the x-axis between when x is 0 and x is 2. Let's start off by figuring out sort of the bounds in which this area of the shaded region has to be in between. Well, we know that the area actually exists, so it has to be between 0 and some other number. So 0 is our lower bound. Our area is at least 0. Next, I've sketched the rectangle that goes from 0 to 2 on the x-axis and 0 to 4 on the y. Therefore, the area of this rectangle is 8, 2 by 4. So we know that the area of our shaded region is less than that. So our area of our shaded region is definitely in between 0 square units and 8 square units. That's the best we know so far. I'm going to call that our okay guess. Do you see a way in which we could again use geometry, the area of a shape that we can easily draw, in order to narrow our guess down even more? I see a way that we could go from an okay guess to a okayer or good guess. The way that we can do that is we can actually sketch the diagonal of this rectangle in order to create a right triangle. Now I've created this right triangle here, and we can clearly see that the area of this right triangle would be half of that, the area of the rectangle, so it would be 4 square units, and clearly our shaded region is even less than that. So we can now confidently say that the area of our shaded region is between 0 and 4. Definitely closer to 4 than 0, but this is a better guess than between 0 and 8. So we're narrowing this down a little bit using geometry. I have one more way that we can use geometry to up our lower bound here. We know we're at least 0, but let's say we drew a square here in this block here that is 1 by 1, and we clearly know that the area of our shaded region is greater than that. The area of the square here, again using geometry, is 1 square unit. So we know that the area of our shaded region in blue is at least 1 square unit because it's greater than that. So we can narrow down our guess of the area of our blue shaded region even more. And now we know that the area is at least 1 and at most 4. Now we could keep going with this idea. What I'm trying to get at here is that because we have a curved function, f of x equals x squared, finding the area beneath it down to the x-axis is not just as easy as geometry. However, calculus does use a lot of the ideas in geometry in order to find the exact area. So far, we have used what we know about geometry to narrow down our area of our shaded region. If you'd like, go ahead and make a guess as to what the actual area is, which we will find soon enough. A common idea in calculus is to use rectangles to approximate the area under a curve. Here I have drawn 4 rectangles. I could have drawn any amount of rectangles, starting at the right, where the top right point of the rectangle is on our curve f of x equals x squared. Now, if we found the area of these 4 rectangles, we would clearly see that it would be an overestimate of the area under the curve. The area of each rectangle, as we know, is base times height. Now I'm writing it as height times base just because that is how we will eventually write this definition, so I'm not just trying to be weird, but that is how we eventually will write it. Either way, we want to take the height of each rectangle and multiply it by the base length. The height of each rectangle is the function value at that x value. So in this case, it's f of 2. This height is 4. In this case, it's f of 1.5. Here it's f of 1, and here it's f of 0.5. So we can rewrite the height is really the f of x value. And how about our base? Our base length is the distance between those two x values. We will call that delta x, or change in x. Now in this case, our delta x, because we've created 4 rectangles, each base length here, the delta x, is 1/2. That is easily found by just looking at this and seeing. However, the way that we can find that is we take our larger x value, in this case 2, minus our smaller x value, in this case 0, and divide it up by how many rectangles we have. So 2 minus 0, the entire length, is 2, divided by 4, the number of rectangles. So we'll have 2 over 4, which is 1/2. Now this next part is a little bit more difficult because while delta x stays constant, it's always 1/2, f of x doesn't. It depends on, the heights change clearly, so it really depends on which x value we're talking about, and this is where the sigma notation can come into play. Let's take a look at how we can rewrite each one of these x values that we want to take the function of to get the height in a different way, but using that 1/2. This length is 1/2 from the origin, so this is 1/2 times 1. We've only gone out one of those 1/2 lengths. Now to get out to this next one, to eventually get the height, this x value can be rewritten as 1/2 2 times to get here. This x value is 1/2 3 times, and this x value all the way out here is 1/2 4 times. In order to get each respective height, we take f of 1/2 times 1 to get this height, f of 1/2 times 2 to get this height, and so on. We are actually taking 1/2 I, where I is 1, 2, 3, and 4. So we actually want to do this 4 different times. The area of our first rectangle would be f of 1/2 times 1, and then times 1/2. This is the height of this rectangle, and this is the base length, delta x, which never changes. Plugging in 2, that will give us the area of our second rectangle. Plugging in 3 gives us the area of this one, and plugging in 4 gives us the area of this final rectangle. We then want to add those 4 areas together. That is where our sigma notation comes in. So we want to start when I is 1 all the way up to 4, because we're having 4 rectangles. This is the height of each rectangle, and this, the base length. Okay, how are you doing so far? Take a mental check here. How did we go from area of a rectangle as height times base to this? This is why calculus is so awesome. All right, I'll stop geeking out. Let's take a look at what f of 1/2 I really is. Our f of x function is simply x squared. So in order to take f of 1/2 I, or if you prefer to write it I over 2, you're really just plugging I over 2 in here for x. So let's rewrite it by actually taking f of I over 2. All right, I have successfully plugged in I over 2 into f of x. So I found f of I over 2 here. So it's squared. Now let's actually square it. So now we have I squared over 4, again times that 1/2. We really have I squared over 8. So what we can do, using those properties of summations, or the properties of our sigma notation here, we can actually pull that 1/8 out front. Now that we have pulled that 1/8 out front, using our properties, remember we just have I squared left, and from our previous video, we learned about these formulas. So take a look back in your notes. This is what the I squared, the sum from 1 to n of I squared equals. It equals n times n plus 1 times 2n plus 1 all over 6. So I'm going to replace I squared with that. And in this case, our n value is 4. So we have replaced this summation with what it equals according to our summation formula for I squared, and n is 4. Simplifying, we will get 15 over 4, which equals 3.75. Now, it seemed like a ridiculous amount of work for finding the area of 4 rectangles. Couldn't we have done that in an easier way? Maybe, but the idea is not just using 4 rectangles. As you can see, using these 4 rectangles and getting an area of 3.75 narrows down what the maximum area of our shaded region could be. It's now less than 3.75 because, as we can clearly see, these 4 rectangles provide an overestimate of the actual blue area. However, what if we created more rectangles and therefore got a more exact value? Before we do that, let's just zoom out and take a look at all of our awesome calculus work so far. Pretty cool. How about 8 rectangles? We can clearly see that these 8 rectangles, once again from the right, are going to again create an overestimate of the actual area of our blue region. However, we are going to get a little bit closer this time than 3.75. Because we have more rectangles, we have a little bit less error. Once again, we're going to use height times base and sum these 8 areas together. Now the base is consistent for each of these 8 rectangles. This time our base is 1/4. That is because this entire length, 2, found by taking 2 minus 0, is divided by 8 this time. So 2 divided by 8 is 1/4. Then, to find all of these specific x values, we've gone out 1/4 once, 1/4 twice, 1/4 3 times, all the way out to 1/4 8 times. Therefore, our x value is 1/4 I, or I over 4, where I spans between 1 and 8. This means we need to write this as a sum starting from I is 1 up to 8, so our n value is 8 this time, of f of I over 4 times 1/4. So again, this f of I over 4, where I is 1 through 8, is the height of each one of these 8 rectangles. Then the 1/4 is the base length of each one of those rectangles. Because our f of x function is x squared, in order to find f of I over 4, we take I over 4 and square it, and then still multiply by 1/4. So we will have I squared over 16 times 1/4. Doing that multiplication will give us I squared over 64. That means we have 1/64, which we can pull out front of our summation. Once again, we have the summation from I equals 1 up to our n value, in this case n is 8, of I squared. So I've once again used the summation formula for I squared, and n is 8 in this case. Simplifying, we'll get 51 over 16, which simplifies to 3.1875. So the total area of those 8 rectangles, again, an overestimate of the actual area we want, is a little bit closer though. It's 3.1875. So let's take a look again at all this awesome calculus we've done. But really, how many times do we need to do this? Well, the only way that we're going to get an exact value of the area of the shaded region is if we keep upping the number of rectangles. If the rectangles are so tiny that they basically mimic this exact curve, then we'll basically get the exact area that we want. But how many is enough? Well, in calculus, that answer is infinity. Okay, so we've finally gotten to the most calculus part of this calculus problem, when we are approaching an infinite amount of rectangles. Now, note that I have not drawn an infinite amount of rectangles because I do not have all the lifetimes to do so. However, we're going to think about this in a more theoretical way. If we were to draw one of those infinite rectangles, what would the length of the base be, aka delta x? And what would the height be, aka f of x? Then we'll sum those infinite rectangles together. Now in this case, because we can't plug in infinity for n when we're actually figuring this out, we are going to just call n, n. Then we'll find the limit as n approaches infinity. So let's think about what delta x is, using how we've figured out delta x, the length of the base of each rectangle, using the way that we've done that in the past two examples when we had 4 and then 8 rectangles. We took the entire length of our base, in this case it's 2, and we divided it by n, the number of rectangles we had. Now in this case, n is just n. We're not plugging in a number for n, so we'll have 2 divided by n. And that's the length of each base of these rectangles. Awesome. Now let's think about what f of x would be, or specifically what this x value would be. Before, it was just the delta x length multiplied by I, where I went from 1 to whatever, either 4 or 8. So, in this case, we'll follow that pattern, and it's going to be f of 2I over n. And in this case, I needs to go starting from 1 and going all the way to n as n approaches infinity. So once again, we can write this as the sum from I is 1 up until n of f of 2I over n times 2 over n. Now in this case, we want the limit as n approaches infinity. Wow, this looks really, really calculus-y. This is pretty cool. All right, let's do what we've been doing. We're going to sort of just ignore this limit out front. We'll keep it there until we can actually utilize it. That'll be the very last thing that we do. Let's focus on what we already know how to do. So we know how to do f of something. F of x, in fact, is whatever gets plugged in. The output is it squared. So we need to square 2I over n. So when we square 2I over n, we will get 4I squared over n squared. Next, we can multiply these two fractions together, so we'll get 8I squared all over n cubed. Now recall, n is just a number. Therefore, it's part of this constant, or rather coefficient in front of the I squared. It's 8 over n cubed. Just like we've been taking these fractions out, these coefficients out front, we can do the same thing for 8 over n cubed. So that way we're left with just I squared in front of our sum. Okay, here we have it. Now, we can rewrite this because we know what this summation formula is. The summation from 1 to n of I squared is n times n plus 1 times 2n plus 1 all over 6. So we've been able to get rid of this sum because we wrote what it actually equaled according to its formula. Now, we're still not going to worry about this limit just yet. Let's simplify this as much as we can. So multiplying this out by doing some foiling and then multiplying the n through will give us, of course, still 8 over n cubed out front. We haven't messed with that yet, nor have we messed with the 6 down here. But we'll end up getting 2n cubed plus 3n squared plus n. Now at this point, we can simplify a little bit, and of course, we still have the limit as n goes to infinity. If you'd like, you can go ahead and simplify 8 over 6 to 4/3. I'm going to do that and then now multiply these two fractions together to get it down to one single fraction. All right, now we have this nice rational function here, and we want to find the limit as n goes to infinity. So what I'm going to do is rewrite this now as 3 separate fractions, each over 3n squared, and then we can do some canceling. Okay, splitting these up and putting them each over 3n cubed. Here, this middle term, 12 over 3, could cancel to 4 over 1. Now we can cancel our n values. N cubed over n cubed goes away. N squared over n cubed becomes 4 over just n. And 4n over 3n cubed becomes 4 over 3n squared. Now we can invoke the limit. Let's think about as n approaches infinity, what this first term will be. Well, our first term is unaffected by n because n is no longer a part of the first term. It is 8/3. The second term, we have 4 over n. And the last term, we have 4 over 3n squared. Now, when we have 4 over something insanely large as n approaches infinity, anything divided by something approaching infinity goes to 0. Think about it. 4 divided by 10,000, 1 million, it's small, very small. So both of these terms, for the same reason, go to 0. Therefore, our final answer is 8 thirds, which is 2.67, actually approximately. What does this mean? It means we found the answer. We found the area of our shaded region is 8/3. Look at all of this awesome calculus work we've just done. We have found the exact area of our shaded region using a limit as n, the number of rectangles, approaches infinity. We used cool sigma notation and some awesome stuff we learned about I, finding and invoking the limit as n goes to infinity. That's awesome. So we have officially found the answer to this question. The area of the shaded region is 8/3 square units. Here's the process that we just completed to find the area of a region under a function and down to the x-axis between two x values. This is just putting it into proper mathematical notation. This is called finding the area of a region under a curve using the limit process. We are saying that the area is defined as the limit as n goes to infinity. Remember, n is number of rectangles under that curve. And then summing from I equals 1 to n the height times the base of each one of those rectangles. The height is defined as f of c sub I. This is new notation that we're seeing right here, and delta x is something we've already dealt with. Now, delta x is just the distance between any two x values. The way that we find that is we take the outer, or the more far right x value, minus the left x value, and divide it by n, the number of rectangles. In this case, n is just going to stay n, because we are evaluating when n approaches infinity. To find c sub I, we can do the following. C sub I is defined as the first x value. In the case of our previous example, that was 0, but it doesn't always have to be 0. Like, we do not have to be finding the area of the region starting at x equals 0. That just happened to be the case. So whatever our lower x value is, we start with that. Then we add on the delta x, or the width of each one of those rectangles, and multiply by I. So this is the way that we find c sub I. And here is the way that we find delta x. So be sure that you have this written down. This part is not necessary to write down. I would write what it is, definition of area. This is called the limit process. This is important to write down. This right here, delta x, and then c sub I. In this example here, we want to find the area of the region bounded by the graph f of x equals x cubed between 0 and 1 and down to the x-axis. This one has already been drawn out for us, and we know the answer is going to be 1/4. We are going to find that 1/4 answer using the limit process. The first thing we can do is simply write out what we know all over here. So we wrote out the area of our region using the limit process. This is the definition. Then we know that since we're finding the area between the x values of 0 and 1, a is 0 and b is 1. C sub I and delta x are defined as these two things right here. So delta x is b minus a divided by n. b is 1 and a is 0, so we'll get 1 in the numerator and of course n in the denominator. Then c sub I is defined as a plus delta x times I. A is just 0, so we don't need to worry about it. Delta x times I is 1 over n times I, which is I over n. So I've just plugged in the c sub I and the delta x. Next, we need to find f of I over n. Well, in our problem here, f of x is x cubed. So in order to find f of I over n, we'll just get I over n quantity cubed. When we cube I over n, we'll just get I cubed over n cubed. Now, in this next step, I'm going to use some of those summation properties, meaning we can take whatever coefficient we have in front of the I cubed and bring it out front of the summation, so in between the limit and the summation. Now, what we have is I cubed over n to the 4th when we multiply these two together. So I'm going to pull out the 1 over n to the 4th out in front here. Remember, n is a number. Yes, it is approaching infinity, but it's still defined as the coefficient of I cubed. So now that we have the coefficient of 1 over n to the 4th pulled out in front, what we can do is simply replace this with one of these summation formulas. From the previous video, we wrote down these 4 formulas. You should definitely have these written down in your notes. And we have not used the I cubed one yet, so this will be our first time using that one. It is defined as such right here. n in this case is actually n. We're not plugging in a number, we're just plugging in n. So I'm going to replace this right here with literally what it equals. N squared times the quantity n plus 1 squared all over 4. So here is our next line. The next thing that we can do is write this as one single fraction through multiplication. So next I did a little bit of work off to the right here in black, multiplying this out, then multiplying our two denominators together gives us this. The very last thing that we can do in order to evaluate as n approaches infinity is break these up into 3 separate fractions. You don't technically have to do this, but it is a little bit simpler. Whoops, this should be n to the 4th here. 1 n to the 4th over 4 n to the 4th. Then this one right here, 2 over 4 can simplify if you'd like to just n cubed over 2 n to the 4th. And then our final fraction will become n squared over 4 n to the 4th. Now we can simplify by canceling the n's. This n to the 4th over n to the 4th simplifies, and then we just have a 1 up in the numerator. So that term is just 1/4. This next term, the n cubed is gone, so it's 1 over 2 and just n. And then this last one becomes 1 over 4n squared. Now as n approaches infinity, which is what we're doing when we're trying to evaluate this limit, as n approaches infinity, this first term is untouched because there's no n values in it. This next term goes to 0. It's 1 over 2n, and as our denominator approaches a very large number infinity, 1 divided by an extremely large number goes to 0. So that is not really a circle, that's my 0. And then this last one is 1 over 4n squared, same reasoning, goes to 0. So our final answer is in fact 1/4. So we answered the question, what is the area of this shaded pink region here? The area that is bounded by the curve f of x equals x cubed and the x-axis, as well as the vertical lines x equals 0 and x equals 1. Now it's saying vertical lines x equals 0 and x equals 1 because that's just another way of saying like the bounds on the left and the right. So a region is at most, well, in most cases bounded by 4 sides, the top, the bottom, which is the x-axis, the left and the right, which are our two x values. So we were able to use the limit definition to find the area of our region, which is 0.25 or 1/4 square units. If we take a look at the actual area here, we can clearly see that if we made this square here, that would be 1 square unit. And then if we halved it, that'd be half of that. This is clearly less than even just half of a unit, a squared unit. So 1/4 is an answer that makes sense graphically. Congratulations on making it through this video and finding area from a calculus perspective. I added this from a calculus perspective because I feel like all of the hard work that we just put in requires a lot more than just the title of area. I mean, anyone can find the area of a rectangle, but can you do it in this fancy of a way? It's pretty cool. Now, just like when we first learned derivatives, I first made you do a limit definition of a derivative with f of x plus h and a limit and all that good stuff. Then afterwards, you learned the shortcuts of derivative rules. This is kind of the same thing. This is the long way of a process called integration, and we are going to be using the antiderivatives and integration rules to do something like finding the area under a curve in a much simpler way. However, in order for you to appreciate that much simpler way, you got to struggle a little bit first. And also, this is pretty cool looking, so nice job.